My name is Alanda Kriener, and today we're going to be going over lab number 3 on determining the unknown mass of a black hole. Picture this. There's a star orbiting a black hole somewhere out there in space, and you're a physicist trying to calculate the mass of the black hole that the star is orbiting around. Here's what we know. We know that the star's mass is to be around 2 times 10 to the 30th kilograms, the star's velocity, momentum, trajectory, and the trajectory time period is 1 day, or 86,400 seconds. And what we're of course seeking is the mass of the black hole. As a little sneak peek, here are the results I came up with, and here's how I got them. In order to calculate this unknown mass, we're going to have to apply some physics. Here we are going to once again be using Newton's second law and the momentum principle, along with the universal law of gravitation and the parallel and perpendicular components of net force. As you know, momentum is the product of mass and velocity, and delta p, or the change in momentum, is equal to the final minus initial momentum. This change in momentum has respective parallel and perpendicular components, the parallel component being in the direction of the momentum and velocity, and the perpendicular component being perpendicular to the parallel motion. We can estimate for a small delta t that the change in momentum over the change in time is equivalent to dp dt, which is equal to the net force, and of course, the mass times the change in velocity over time. Since F net is composed of the perpendicular and parallel components of net force, so is dp dt. Using the product rule, the parallel component of dp dt is equivalent to d magnitude of p dt times p hat, and the perpendicular component is equivalent to the magnitude of p times d p hat dt. The perpendicular component of an orbital motion is also equivalent to mass times velocity squared over r, the radius of the kissing circle. The parallel component of F net represents the speeding up and slowing down of an object, while the perpendicular component represents the change in direction or curvature of the object. So what does this all mean? Well, like I mentioned before, the parallel component of dp dt, or dp dt parallel, is parallel to the momentum and velocity and is representative of the object speeding up or slowing down. Contrastly, the perpendicular component of dp dt, or dp dt perpendicular, is perpendicular to the object's motion and velocity and is representative of the curvature of the motion. It's important to note when computing the parallel component of dp dt that you compute the derivative of the magnitude of momentum and not the magnitude of the derivative of momentum, as in this part of the calculation, we are only observing how fast the momentum changes, disregarding direction because that is a part of dp dt perp. As you can see with this example, when the final momentum is greater than the initial momentum, dp dt represents a speeding up of the object. Going the other way around, when the final momentum is lesser than the initial momentum, the parallel component of motion shows the object slowing down. When there is no change in the momentum of the object, there is no change in speed, and the object accelerates uniformly, and dp dt parallel is 0. As we have seen previously, the universal law of gravitation is represented by the equation Fg equaling to the product of the masses and the gravitational constant over the distance between them squared, and multiplied by the negative r hat, or position vector between the objects. In order to solve for the mass of the black hole, aka m2, we have to isolate it on one side of the equation that we will then plug into our code. Now it's time for the actual calculation to be made using a computational model. Here we are using a code in which we only need to alter a few things, as the trajectory and ellipse path are already coded. First things first, I entered my email address into the seed of the code to ensure a unique trajectory of my star. Next, I inserted the given mass of the star in delta t of 1 day, or 86,400 seconds. Next, I inserted the final and initial momentums using the given final and initial velocities respectively and multiplying them by the mass of the star. Then I inserted simple final minus initial equations for both the velocity and momentum to get delta v and delta p. As we discussed earlier, the net force, aka dp dt, is equivalent to the change in momentum, or delta p, over the change in time, delta t, which is specified in this line of code. We then specified dp dt as equal to F net. Next we code dp dt parallel by setting p hat equal to the unit vector of initial momentum, with initial momentum being divided by its magnitude. We then calculate the change in magnitude of p as being the final magnitude of momentum minus the initial magnitude of momentum over delta t. And finally, we get our dp dt parallel component to be equal to the product of p hat and the change in magnitude of p. We then specify, since this force from the black hole is the only assumed force on the star, that F net parallel is equal to dp dt parallel. Since we know that F net is equal to dp dt parallel plus dp dt perp, we can solve for dp dt perpendicular, knowing F net and dp dt parallel by subtracting dp dt parallel from F net to get dp dt perpendicular. Lastly, we can specify that F net perpendicular is equal to dp dt perpendicular, since the force from the black hole is the only presumed force acting on the star. In order to use the universal law of gravitation, we need to distinguish the vector r pointing from the origin, aka the black hole, to the position of the star. I then set MBH, the mass of the black hole, equal to the universal law of gravitation with m2 on one side of the equation, like we did earlier to solve for the black hole's mass. Finally, I added arrows in an arrow scale to show the direction and magnitude scaled with a very small number of 1 times 10 to the negative 17 of net force and its parallel and perpendicular components throughout the trajectory. Here is a snapshot from my final computational model, and as you can see, the mass of the black hole is calculated to be around 1 times 10 to the 34 kilograms. So what if the black hole was removed and a different black hole was placed in the same location, and the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole? Could you tell the difference? The answer is no. If r remains the same and the star's trajectory and motion remains the same, the net Fg causing that motion is the same, and therefore will calculate the same mass of the black hole. In conclusion, we discussed that force can be broken down into parallel and perpendicular components, where the parallel component represents the change in speed of the motion, and the perpendicular component represents the change in direction or curvature of the motion. This net force, or dp dt, can be seen as the change in momentum over the change in time, which is equivalent to dp dt parallel plus dp dt perpendicular. Additionally, we use velocity and position update and manipulated the universal law of gravitation to solve for an unknown mass of the black hole, given its star orbit's trajectory and motion, which ended up to be approximately 1 to the 34 kilograms.